Hello and welcome to Physics 2212 Lab 4, bar magnets. The purpose of this lab is to investigate the strength of a magnetic field from a bar magnet with respect to distance. It is also to compare a computational model with experimental results. Starting off with some key principles, the magnetic field strength from a magnetic dipole is given by the following formulae as measured from the axis and perpendicular to the axis of the dipole. The magnetic field due to a bar magnet is given by the following equation where K and N are both constants. The magnetic field of a magnetic dipole is given by the equation at the bottom. For this experiment, we will be modeling the bar magnet as a magnetic dipole. Several key assumptions we are making are that the bar magnet behaves as a magnetic dipole and that there is little to no magnetic interference from any metal objects nearby. For a brief preview of the results, the calculated magnetic dipole moment was 0.9616 amp meters squared, and the simulated magnetic field for the off-axis measurement had a magnitude of 19.6 microtesla. On the other hand, the experimental magnitude for the off-axis measurement had a magnitude of 72.4 microtesla. For the procedure, we found the magnetometer chip on the phone and aligned the magnetometer with the Earth's magnetic field such that the component of the magnetic field reads 0. We then measured the on-axis magnetic field and distance for the magnetic field readings to be 20, 70, 120, 170, and 220 microtesla. We then measured the off-axis magnetic field. This was done by measuring the on-axis distance where the magnetic field was 100 microtesla. We then applied this distance to the y-axis and measured the magnetic field at this point. Here are the experimental results from our measurements. Here the data was linearized and a regression was carried out. More specifically, the following equation was used in performing regression on the data. The constants were then used to solve for the magnetic dipole moment as shown in the bottom equation. The magnetic dipole moment was then calculated to be 0.9616 amp meters squared. For the computational model, we first initialized all of the necessary parameters. Next, we defined the function to calculate the magnetic field due to a dipole. Next, we defined the observation positions for which we will be calculating the magnetic field. Next, we draw two arrows for the on-axis measurements. Next, we draw the four arrows for the perpendicular measurements. And finally, we calculate the magnetic field for the off-axis measurement. Here are the results from the computational model once the simulation is run. Here the blue arrows represent the perpendicular measurements, whilst the red arrows represent the on-axis measurements, and the magenta arrow represents the off-axis magnetic field. Here the simulated magnetic field for the off-axis measurement had a magnitude of 19.6 microtesla. The experimental magnitude for the off-axis measurement had a magnitude of 72.4 microtesla. This large error can be due to interference from nearby metal objects, inconsistent placement of the phone, and extremely sensitive magnetometer readings. If we hadn't oriented our experiment to compensate for magnetic north, then the Earth's magnetic field will have made contributions to our x and y-axis measurements, instead of just to our y-axis measurements. This makes it more tedious to compensate for Earth's magnetic field. If we had stuck two identical magnets together and ran the experiment again, you can expect that the fields from the two identical magnets would add to give a magnetic field that is twice as strong as before. The measured distances for each magnetic field strength would increase. This is because the stronger magnet does not need to be as close for it to have the same magnetic field strength as a weaker magnet.